So last time we wrote this algorithm, which is L-cube's reduced basis algorithm. So what it does is that B1 to Bm are the linearly independent vectors that span a given lattice. Your goal is to find an approximation to a shortest vector by the lattice generated by these vectors B1 to Bm. So first, in step 1, you compute the Gram-Schmidt orthogonalization of B. So the output of that will be B1 star to Bm star, and then the relative these projection constants would be mu ij's. Okay, so these two are the standard output, the data which you get out of GSO computation. And then what is done is this mu ij is rounded off to the nearest integer, because mu ij may be a real number, it may not be an integer. So this computation you actually cannot do by remaining within a lattice. Okay, so and you really want to remain in the lattice generated by B1 to Bm. You don't want to go out. You don't want to change the lattice. So instead of mu ij, you will calculate the nearest integer, and then you will only use an approximation of mu ij. So that will be the new vectors B1 to Bm. They still generate the same lattice. Now that was the first condition for reduced basis. The second condition was that, if you recall, the second condition of reduced basis was this, that is written in blue, that that is written in black, point number 1. So point number 1 wants essentially this C1 star to Cm star in sort of an increasing order, right? Because you want to output in the end C1 star. So ideally C1 star should be smaller than C2 star, should be smaller than C3 star, and so on. That may not be achievable efficiently. So there is an approximation here. You want Ci star to be smaller than 2 over square root 3 of C2 star. C1 to be smaller than 2 by square root 3 of let's say C2, then C2 to be smaller than 2 by square root 3 of C3, and so on. So it will be roughly in an ascending order. Now if this condition is violated till now, when you come to step 3, suppose this condition is violated by some Bi, meaning that Bi star's length is bigger than this bound on Bi plus 1. Okay, so if this happens, then the simple correction is swap them. Okay, so Bi plus 1, Bi did not satisfy the condition, but maybe when you swap, Bi plus 1 will satisfy the condition with respect to the next. But then since you have changed the order of the vectors, you have to recompute GSO. So go to step 1. Okay, and keep doing this. Hopefully this will terminate after finite number of steps, and then you will output B1 to Bm. Okay, so the analysis of this algorithm is key. First of all, why will this algorithm stop? If it stops, in how many steps? And when it stops, is B1 the correct approximation of shortest vector? Right, those are the questions to be answered yet. So let us start with the analysis. So step 2, step 1 is just GSO, that you understand, that is standard. So what happened in step 2? In step 2, we recalculated, or we changed B1 to Bm following GSO, but remaining in the lattice, right. So the new B2, for example, is B2 minus this projection constant rounded off. Times B1, right. This is the new B2. So note that if you look at the new projection constant B2, B1, right, this has become, so this is B2, B1 divided by norm of B1 square minus B2, B1 norm of B1 square times B1 comma 1 divided by norm of B1 square. But this last quantity is 1, right. So you see that you are actually subtracting B2, B1 over B1 square, the old one. From that you are subtracting the nearest integer. So the difference will be smaller than half. Okay. So this value, or let me be precise, let me call this new mu2 1. So mu2 1, its absolute value, so it is between minus half and half. Okay, the absolute value is less than or equal to half. This you can check. And so on. So what you have ensured is that mu ij, step 2 ensures that mu ij is at most half in magnitude. For mu I minus 1. Okay. So this property is true for all I by the same argument. Also, the transformation that you are doing is this, right. This is the transformation. Now this transformation is just subtracting a multiple of B1 from B2, it is not scaling B2. So since it is not scaling B2, this is unimodular and the lattice does not change. Okay, so the lattice remains unchanged after this transformation. So step 2 is good, we understand that. What is step 3? Now in step 3 what you did is, if this reduced basis condition is violated, so this LHS is bigger than RHS, then you will swap the two vectors and you will repeat the algorithm, go to step 1. So to show that this number of repetitions is bounded, that it's not repeated, to show that it's repeated few times, we need a potential function. Okay, so what will be the potential function? Potential function should be such that to begin with it is small, and with every swap and repetition it reduces. So we will use the following potential function. It will be the product of the lengths of bi star but remember you want this thing to reduce with every swap. So intuitively what was happening, bi star, some bi star was larger than bi plus 1 star intuitively, right? So when you swap, for this to be reducing significantly, let us give bi star and bi plus 1 star different weights. So for that we put an exponent here. Okay, so it's actually bi star will get a larger exponent than bi plus 1 star. Okay, so when you will swap, this value will actually fall by how much? So we will now calculate that. So step 2 has no effect on this. Why? So step 2 was mimicking GSO, and this potential function actually looks at bi star. So these axes, these orthogonal axes do not change with GSO. So let's remember that. So step 2 has no effect on this, while each step 3 repetition of step 3 swap reduces D by a factor of, so bi star is being replaced by bi plus 1 star, and bi star has more weight, right? So the reduction is by this factor. And now by the reduced basis condition violation, you know that bi star was actually bigger. So this is less than 3 by 4 minus mu I plus 1 I square. Now mu square is at most 1/4. So this is less than what? This is less than half. Sorry, no, mu square is it is non-negative. So this is actually less than 3/4 even. Okay, so D will, with every swap, D will reduce by a factor of at least 3/4. Okay, what else? So what was D to begin with? And more importantly, was D an integer or a non-integer? See, if it is an integer, then you know that if after every swap it remains an integer, then you know that you can only hit 1, you cannot, the potential function cannot go below that, and then you will get a bound. If it is a real number, then it can keep on reducing infinitely many times. So we will actually show that at any point of time d is an integer. So that is an important property of the potential function. The magnitude of d is a positive integer of value less than 2 raised to O tilde n raised to 5L. Okay, n was the ambient dimension that you started with of the lattice or the vectors. L was the coefficients, the coordinates in the vectors were L bit. So we have a bound actually, n raised to 5 times L. This is the bit size bound on the potential function, and it's an integer. Since every time you are reducing it by 3/4, this gives you number of times n raised to 5 times L. Okay, so that will be the immediate consequence of this lemma. So why is this true? Let's prove it. So write d as product of dj j1 to m minus 1, where dj is simply a product of bi star lengths. Okay, so instead of these exponents that we put, we are removing the exponents essentially. So we are just multiplying b1 star length to up to bj star length, squaring it. That is dj, and you can see that d is equal to product of dj. dj has a nice interpretation. If you think in terms of orthogonal axis, if you multiply the length of the axis, this represents some kind of a volume. Okay, so the potential function d is actually a product of volumes of let's say subcubes or subparallelepipeds. So dj relates to the volume of b1 to bj. Because dj is the determinant of b1 star to bj star. So this is a sequence of column vectors. Transpose it so they become row, multiply it with this. So dj is actually the determinant of this matrix. This matrix is just remember that b1 star to bj star are orthogonal. right. So, B1 star inner product B1 star will be the length of B1 star square, but other inner products will be 0. So, this is actually a diagonal matrix, and determinant is just the product of Bi star square, which is equal to which is a diagonal matrix and equals. Now remember that B1 star to Bj star are computed by GSO, so they only depend on B1 to Bj, right. So, B1 star to Bj star are just a transformation on B1 to Bj. So, we can rewrite it as B1 to Bj times a matrix transformation and itself. Right, C is the unimodular transformation. So, this is a nice transformation happening in the lattice. Well, not quite, but it's a basically it's a transformation. GSO is a transformation such that determinant of C is plus minus 1. So, if you look at the determinant version of this, then you will get that dj equals, so determinant of C and determinant of C transpose is plus minus 1, so the product is 1, right. So, ultimately it is the determinant of B1 to Bj transpose times B1 to Bj, determinant of this matrix, square matrix, which is, now remember that B1 to Bj are given in the input, so they are integral entries. So, the determinant of this integral matrix is integral. Moreover, since the vectors were linearly independent, this will be, this cannot be 0, B1 to Bj are linearly independent, right. So, the volume will come out to be a positive integer, and the bound follows from just look at the entries of Bj, they are L bits. So, you will get, actually for this you have to go back to the first algorithm. How did you come from polynomial factoring, integral polynomial factoring to this B1 to Bm instance of SVP, right. So, there was this NQ-Bell times Hansel lifting that we did. So, the integers after that will potentially grow to 2 raised to O tilde NQ-Bell. So, this is the magnitude of the numbers, integers you have in vectors B1 to Bj, and then when you take determinant, you will be multiplying these j times. So, you get times raised to j, okay, and j remember is at most m, which is at most n. So, this implies that d, the potential function, is less than 2 raised to O tilde NQ-Bell times, so you just multiply for over j going from 1 to n, so it gives you another n square. Okay, so that's a bound. That's a lazy bound on the potential function, which proves the lemma. So the potential function is a positive integer of value less than 2 raised to O tilde n to the 5L. Okay. So now we have what we wanted. We are nearing the end of the proof. So thus step 3 repeats at most O tilde n to the 5 times L times in L cube algorithm. And gives the reduced basis. In fact, reduced basis may be many, so you will get R reduced basis. And why is that? Well, you showed how many times step 3 will repeat. Once step 3 doesn't repeat, it means that that both the axioms of reduced basis in the definition are satisfied. So then you will output the reduced basis. So basically the vectors b1 to bm are now approximately ascending order, and the other condition was that if you look at the projection constants, they are around half. Okay, so this is like an approximation to GSO. They are kind of pseudo orthogonal. So you will just output, so you can pick B1 in the output. That's a SVP approximation. So this we have done last time. Right, last time we showed that C1 estimates the shortest vector by this factor. We had shown this. Right, so just recall this identity or this inequality, that C1 star will be a 2 raised to m by 2 factor. So B1 is an 2 raised to n by 2 approximation of the shortest vector. Okay, so we have everything that we wanted, finishes L cube. Let's see the time complexity. So just a naive time estimate, a crude time estimate of the polynomial factoring algorithm is n raised to 5L. So you have to start from the very beginning. How did you do Hensel lifting, and then you reached this lattice instance, and then you applied L cube algorithm. So this will be n raised to 5L. These are how big the numbers are. This actually is the number of times you are repeating the L cube algorithm. The first steps you are repeating n raised to 5L times. Okay. What happens in this step 2 is that this is already a for loop, nested for loop, and when you are doing this difference bi minus bj, remember there are n coordinates, right? So overall step 2 takes n cube naively, a naive analysis. So that's another n cube. And how big are these integers on which you are computing? That's around n cube L. So you get O tilde n raised to 11 L square. Okay, so this is a horrible time estimate. It's n raised to 11 times L square. So as the dimension increases, this algorithm is extremely slow. You can optimize some parts of it, but you cannot make it very fast, at least not theoretically. But on practical instances, it is known to work well. Okay, so this is used in practice, some version of this. So this comes from the number of repetitions. This n cube is step 2, and this is the size of bit size of integers. Okay, so that's the time complexity of integral polynomial factoring. And if you just look at L cube algorithm, so to find reduced basis, what is the reduced basis finding algorithm's complexity? So assume big L to be the max bit size in BIs, L cube algorithm approximates in how much time? So this will be bit size of the integers times m, and every vector there m of these, or this actually is no, not like that. This is m is for pre-processing times m square whole square. So you get L square m to the 6. So let me give an explanation for this. So this is the bit size, but this m we are putting for pre-processing. And this m square you will get because of the number of times step 3 will repeat. This comes from the potential function. So you can think in terms of the bit size. You started with L bit size. When you did the pre-processing, you had a growth of multiplier m, and when you started repeating step 3, there was another blow up in the bit size by m square. Okay, so this is what the integers, these integers are this big, and so that also tells you how many times you have to repeat as step 3. So you square it. Okay, so this is a crude estimate. In terms of m, it is taking m to the 6 time. So let me finish L cube algorithm by giving some properties that it satisfies, its output satisfies. So L cube algorithm and reduced basis is used in many places. So, examples are computational problems in algebraic number theory, faster arithmetic in number fields, knapsack problem, and so on. The key properties of this reduced basis which are useful there in these applications is the following. So, let me collect that here. So, let B1 to Bm be a reduced basis of the lattice L, which is in the ambient space, let us say Z to the n, and B1 star to Bm star be the GSO. After GSO, you get B1 star to Bm star on this. Then the things which are satisfied, and these properties you can deduce from the calculation that we just did. Okay, the calculations we did in the last two lectures, using that you can deduce these properties. First property, in fact, we deduced, it says that the length of Bj never exceeds the length of so Bi minus 1, let us say j equal to Bi minus 1. Bi minus 1 is at most Bi star times 2 raised to I minus 1 by 2, okay, for all j behind I. So, in particular, it is saying that if you look at Bi minus 1, it is a factor smaller than Bi star, and this factor is exponential in I, 2 raised to I by 2. This can be shown by this inequality axiom, this almost ascending property of the reduced basis. Okay, it follows directly, we did that calculation. Second is if you look at the product of Bi's length, I think for this I needed n would be simpler, B1 to Bn, B1 star to Bn star. There is no m, or m is equal to n. So, this product of Bi of the reduced basis, if Bi's were orthogonal, this would have been the volume of the lattice, right? The volume of the lattice is the same as the determinant So, the product of these BIs is at least the determinant of the lattice, and it is at most this multiple 2 raised to n minus 1 by 4 times dl. In other words, if you look at the product of the lengths of the vectors in the reduced basis, this is an approximation of the determinant. Okay, it's a 2 raised to n square approximation. This basically intuitively what it is saying is that the B1 to Bn that you get are pseudo orthogonal. Okay, so their product also is not very far from the volume. Third is that B1, right, which is the vector you pick and output as an approximation of SVP. This is then related to the volume. Like this. So, one can be obtained, can be proved, inequality 1 can be proved by the inequality axiom of reduced basis. From that, it easily follows that product of BI is related to the determinant, and from the determinant then you can deduce something about B1, because you know the relative ratios of BIs, BI lengths. So, from that you will get actually that B1 is basically it is smaller than in step 2 in RHS, look at 1 by nth power. Okay. At this point I would like to remark that the shortest vector in the lattice has length around square root of n times the volume by raised to 1 by n. Okay, this is a result by Minkowski. This is a classical result that shortest vector in lattice has length around the volume raised to 1 by n times square root n. So, if you look at B1 that you are outputting, this is close to that, it is only off by 2 raised to n by 4. Okay, so, again this is an exponential approximation, but theoretically it is connected to many things. So, I will not go into the proofs of each of these, I leave it as an exercise. So, one you prove by use this condition in the reduced basis, condition number 1. Reduced basis definition. For the second one, this relationship with the discriminant, just use the above and the fact that the discriminant or volume is product of, it is the determinant of this matrix. okay, which is then less than equal to product of the lengths. And then you can use again inequality 1, which will relate bi star with bi. So that is how you will get inequality 2. Inequality 3 will follow by the ratios of bi's. So by 1 you get that P1 length is less than equal to two raised to I minus 1 by 2 times Pi star, right. This is what inequality 1 gives you for all I. So using this and inequality 2 that you got, you will get 3, and the fact that product of bi star over all the i's is product of bi star square is dl. Yeah, that is true because bi stars are orthogonal. Okay, so I should have made this an equality actually, that's true, which is also the volume. Volume of the lattice. Yeah, so using the same fact and this inequality 1 will give you inequality 3. Okay, so these are the 3 properties which are always invoked in the applications, major applications. So one application where I can stop now is given rationals alpha 1 to alpha n and epsilon, find integers p1 to pn q such that pi by q approximates alpha I. And minimize q. Okay, so you are given these rationals alpha 1 to alpha n and you want a rational representation for all these alpha i's. The catch is that denominators should be the same. Okay, so this problem is called simultaneous Diophantine approximation, and Diophantine because you are given these rationals, let us say alpha 1, and you want to write it as P1 over Q, and simultaneous because you are given alpha 1, alpha 2, and you have to simultaneously express it as P1 by Q and P2 by Q. Now obviously Q exists, but then it could be very large if you do it naively. Okay, you want to minimize Q as much as possible, and this problem surprisingly could be solved in polynomial time using reduced basis L-cube algorithm. Okay, so this also I will leave as an exercise. So solve it by L-cube reduced basis algorithm. Okay, so with this I will stop the discussion on L-cube algorithm, and I will move to an application in security. Okay, so we will look at a public key crypto system. Which will be lattice based. So what is a public key crypto system? So this is a mechanism that is used in a number of situations. One simple example is when you interact with your bank. Okay, so bank has given certain information to the public, using which you can send your private information to the bank, which only the bank can understand, nobody else could understand over the internet. So let us fix that example. Example is communication between bank and client, and obviously it should be secure communication. So one public key crypto system which is used quite commonly is RSA. But the problem is that it is insecure if quantum computers exist. Now in the future, quantum computers may exist. So people believe that we should have a mechanism which can even which can work even if quantum computers are created in the future. Okay, so for that lattice based methods are used. This is why this is a major application of lattices. Not only security in quantum computers, but there are also other advantages for using lattice based cryptography. So lattice based methods are quantum secure. Okay, so there are many systems proposed. We will see here the basics of Ntru, NTRU crypto system. So NTRU was proposed by Hofstein, Pfeiffer, and Silverman. In the conference Crypto in 96. Okay, and this the basic protocol is very popular, and there are a lot of variants of this known, some of which are also implemented, and they work well. So Ntru stands for nth degree truncated polynomial ring. Okay, so NTR. So what is this polynomial ring? This is very simple. It is just integral polynomial ring mod out x by x to the n minus 1. Okay, so this is a lattice. It's an n-dimensional lattice, and all the computations will happen here. Okay, so the message, the private key, the public key, they will all elements of this ring. So they will all be lattice elements, and we'll do computations with them, simple computations. Okay. So NTRU's security relies on the fact that the L-cube algorithm cannot approximate SVP fast enough. For large n. So, or maybe I should say for large 2n, and n will be taken let's take n to be 251. Okay, so n is 251 means that 2n is 500, and we have seen that the complexity of L-cube reduced basis algorithm is something like 500 to the 6 times other factors, and that in practice actually will be very slow. Okay, and as you increase n, it will get harder. The L-cube algorithm will become slower. So one advantage of this is that it allows smaller key sizes than RSA. So to get the same security, same level of security, RSA would require thousands of bits, but here you can do in 200, 300, 400 bits. Okay, so the key sizes will also be small. So there are many advantages in this system. Let us quickly go through the public key, private key, encryption and decryption. So what are the public parameters? that the bank will release. Okay, so bank releases n and prime powers pq. Okay, so you can keep this example in mind. N pq, n is 251, p is 3, q is 2 raised to 7. So 128. Okay, and the bank releases support bounds. So these are just numbers, we will call them df, dg, dm, dr. Okay, these are around, again example, numbers around 80. So they are not very large. So this is what the bank fixes and also publishes them on the website. What is the private key? So private key of the bank. What does the bank keep private and will not publish? So this is pick random polynomials f and g in R such that so f has exactly df ones and one less minus ones. Gx on the other hand as equal ones and minus ones. Okay, so again f has df, which is the parameter published by the bank, that many ones, and minus ones are one less. So this means, this immediately means that f at 1 is 1. G on the other hand has equal number of ones and minus ones. So G at 1 is 0. Okay, so randomly these polynomials are picked. There is a lot of choice because if you take df dg to be 80, then there are around 80 positions to be picked out of n positions, right? So 80 positions out of 251. And even after picking the positions, you still have to decide on plus minus 1 sign. So there is a lot of, there are at least, I would say 2 raised to 80, at least 2 raised to 80 possibilities are there. And bank picks one of them and keeps it private. And what is the public key which the bank releases? So public key, it uses f and g to compute g by f. So compute G by F mod Q and publish this. One thing I would like to say here is that this mod Q computation you should reduce numbers to plus minus Q by 2. Okay, so you have coefficients between minus Q by 2 to plus Q by 2. That's your Hx. Bank publishes it. Note that from H, it is not clear how to compute G or F, right? Because H is G by F, there are two unknowns. So from H, it is not clear how to find those two unknowns. So they seem to be still a secret. So next time we will see how to do encryption and decryption. Okay, and talk about the security of this vis-a-vis L-cube algorithm. Okay, stop. Thank you.